Hello, everyone. Welcome to Brain Blitz Audios. Today, in this episode of Mind Maps, we'll be dealing with the 8th chapter in the grade 12 syllabus for chemistry in CBSE. The name of this chapter is the D and F block elements. And as usual, we'll be enlisting the help of this mind map in order to explain the chapter. Mind maps are easy tools for last-minute preparations. However, they can be pretty extensive, and therefore this video is devoted to explaining this mind map in some detail. The chapter that we're dealing with is the D and F block elements. So when we're talking about the D and F block elements, we'll be essentially dealing with the middle elements of the periodic table. To the left, the first two groups were those of alkali earth metals, the S block elements. And the final 6 groups to the right talks about the P block elements, while the groups 3 to 12, they house elements called the D block elements, and since they are present between the S and the P block, and they are a transition between S and P, they're also called as transition elements. So today we'll be talking about the D block transition elements, their properties, and some of their general characteristics. And then we'll be looking at oxides and oxoanions of some of these metals. Then we'll be looking at the F block transition elements. We'll be studying lanthanoids and actinoids separately. Then we'll be looking at lanthanoid contraction, which is a phenomenon occurring in D block and F block elements related to atomic size. And finally, we'll be looking at the uses of the D and F block elements. So let's move on to our first topic, the D block elements. These are the elements, the transition elements, comprising group 3 to 12 in the main periodic table. So their position is between the S and P blocks. These transition elements have an electronic configuration of N-1 D1 to 10 and NS1 to 2. They have many physical properties, and most of the time they show typical metallic properties such as melting point and boiling point being high enthalpies of atomization, etc. Now these elements, they decrease in radius with increasing atomic number, and this is due to a phenomenon known as lanthanoid contraction due to imperfect shielding. Now, in D block transition elements, the ionization enthalpies, they increase generally from left to right. However, this trend is not constant. In the middle, you can find some elements which have lower ionization enthalpies than expected, and some others which have higher ionization enthalpies than expected. So this gets varied, but in the end, if you're looking at a general trend, then you can say that ionization enthalpies increases from left to right. Now, another fascinating thing about the D block elements is that they have variable number of oxidation states. And in other metals, while the lower oxidation number is stable, in D block and transition elements, the higher oxidation number is stable. And when we're talking about trends in electron potential from M2 plus to M, these are negative for the metals manganese, nickel, and zinc. So for these 3 elements, the trend in M2 plus / M electron potential is more negative than we expect. And another trend, which is variable in all kinds of transition elements, is the trend in M3 plus to M2 plus electron potential. So this is always variable. So these are some of the physical properties. Next, we're looking at chemical reactivity. So chemical reactivity and standard electrode potential values. The reactivity of D block transition elements, they are variable and they form separate amount of oxidation states. So for example, Ti2+, V2+, Cl2+, etc. in terms of chemical reactivity are strong reducing agents. Another point about oxidation states is that these have many number of oxidation states possible, and the highest amount of oxidation states is for manganese. It has +2, +3, +4, +5, +6, +7, So these are the oxidation states. Now let's look at magnetic properties. Depending on the configuration in the D block element, the magnetic property changes as well. Some of these elements, such as zinc and say chromium, they are diamagnetic because they have paired amount of electrons. All electrons are paired. While most of the other atoms, they are paramagnetic, which means that the electrons are not paired in the orbital. In some extreme cases, we can find ferromagnetic elements as well, such as iron, nickel, copper, cobalt, etc. Copper is paramagnetic. The magnetic moment increases with the increasing atomic number. So as the atomic number increases, you have more electrons coming into the d orbital. So a lot of them are paramagnetic. A lot of these elements are paramagnetic because of the unpaired d electrons. Another interesting fact about d block elements is that they form colored ions. So in the aqueous state, if you look at a solution of a solution containing a D block element, then most likely it is colored. For example, CuSO4 or copper sulfate is blue in color, and that's why it's called blue vitriol. Now, they form colored compounds due to DD transitions. Now, the reason here is that we have, say, an s orbital and a d orbital. Then the point is that the energy difference between the S and D orbitals is very less. And even among the d orbitals, the energy between them to change an electron is very less. So these compounds, they can form colored, these elements, they can form colored compounds due to constant transition of electrons within the d orbital and also from d orbital to s orbital. That's what brings about the color. Now, they also form complex compounds. These are a special class of chemical compounds that we'll be studying in the next chapter. For now, you can say that these are compounds which are not dissociating in an aqueous medium. For example, we have FeCN6, say 3-. This is a coordination compound, a complex compound. So the D block elements, they form a large number of these complex compounds because, again, of their variable oxidation state. More of this phenomenon will be studied in the next chapter. Then we have catalytic properties. We constantly use D block elements as catalysts due to their variable oxidation states and their ability to form a lot of complexes. These D block elements are also able to form interstitial compounds. These are non-stoichiometric and neither ionic nor covalent. And since D block elements have almost similar atomic sizes due to lanthanoid contraction, you can form alloys easily with D block elements due to their similar atomic sizes. So that was a short overview about the D block elements, their physical properties, their chemical properties, and also about some unusual things regarding the D block elements. Now let's look at some oxides and oxoanions of D block elements. The first is potassium dichromate, K2Cr2O7. Now, how do you prepare this compound? The fusion of ferric chromite ore with sodium carbonate in excess of oxygen produces yellow solution of sodium chromate, ferric oxide, and carbon dioxide. Ferric chromate is fused with Na2CO3, that's sodium carbonate, and there is an excess of oxygen. So this yellow compound here is sodium chromate. And this sodium chromate also forms ferric oxide, Fe2O3, and carbon dioxide as a byproduct. Now, we're asked to form potassium dichromate. Now, sodium dichromate is more soluble, so therefore we try to form potassium dichromate by filtering and acidifying the yellow solution of Na2CrO4. So when we're acidifying and filtering this compound, we get an orange solution in which sodium dichromate is present, and this sodium dichromate can be crystallized. Potassium dichromate can be formed by treating sodium dichromate with KCl with NaCl as a byproduct. So when sodium dichromate is reacted with KCl, it's treated with KCl, you get potassium dichromate, and the byproduct is sodium chloride, common salt. Next, properties. Potassium dichromate can be described as a strong oxidizing agent, and it is used in organic chemistry. So you can see a lot of times we use potassium dichromate as an oxidizing agent. And you can see its action in an acidic medium. So the chromate dichromate ion in presence of acid and electrons changes to chromium 3+ and water. That's why this is a strong reducing agent. It gets oxidized. Now, the reducing power of dichromate ions are so great that it can oxidize iodides to iodine, hydrogen sulfide to sulfur, SO3 2- to SO4 2-, and NO2- to NO3-. And we also have a structure of a dichromate ion. So you have six O3 oxygen atoms bonding with chromium on one end, and on the other end you can see a bond of 179 picometers with the central oxygen atom. Now, the bond angle between these two bonds is 126 degrees, and the bond length between the chromium and the outer oxygen is 163 picometers. And the overall charge of this ion is -2. That's why you have two potassium atoms with a dichromate ion. So potassium dichromate. Next, we'll move on to another more powerful reducing agent. This is known as KMnO4. This is an oxide of potassium. So KMnO4. How do you prepare KMnO4? KMnO4 is prepared by the fusion of MnO2 with potassium hydroxide, which is an alkali metal, and an oxidizing agent like KNO3. So MnO2 is fused with an alkali metal hydroxide. For instance, here we are using potassium hydroxide, and there's oxygen as well in order to form 2K2MnO4 plus 2H2O. So this compound is dark green in color, and 2K2MnO4 is now disproportionated in neutral or acidic solution in order to give the permanganate ion. So now the permanganate ion we get, and then when it binds with potassium, we get KMnO4. So what we essentially had was MnO4 2-, which when reacting with an acidic medium becomes MnO4-, and with excess of MnO2 and water. And this Mn2+ also gives it directly. So if we have magnesium ions, manganese ions, then in the lab you can take manganese 2 ions, and a salt of this ion is oxidized by peroxodisulfate, which is S2O3. So peroxodisulfate oxidizes manganese 2 ion to give you a direct permanganate ion. Now, properties. Now, the properties of potassium permanganate is that it has an intense purple color, and It is also paramagnetic, but it's weak temperature dependent. The paramagnetism in KMnO4 is weak temperature dependent. Again, it is a very good reducing agent because it easily gets oxidized to Mn2 plus ion and water. It is so good as a reducing agent that it can oxidize an iodide ion to iodine, a ferrous ion to ferric, and then it can also oxidize C2O4 minus to carbon dioxide, S2 minus to sulfur, SO32 minus to SO42 minus, and NO2 minus to NO3 minus. So we can consider KMnO4 as a strong reducing agent. So that was how we completed the D block elements. The second part of this chapter deals with the F block elements. The first kind of F block elements are lanthanoids. Now, these are a set of 14 elements that occur after lanthanum, whose outer electron goes into the F orbital. So therefore, since there is no space in the current periodic table, the lanthanoids are written below the main periodic table. So they have an electronic configuration of 4f1 to 14, 5d0 to 1, 6s2. And the reason why 4, 5, and 6 is because we're dealing with lanthanoids. When it comes to actinoids, it becomes 5, 6, and 7 respectively. So this is the electronic configuration of lanthanoids, starting from lanthanums and ending at lutetium. So in a discussion of lanthanoids, we usually include lanthanum even though it is not part of the subdivision of F block elements. Now, when we're talking about atomic sizes and ionic sizes, these decrease from lanthanum to lutetium because the F orbital to which the electrons are going into has negligible shielding effect. When we're looking at oxidation states, the most common oxidation state, which is present across the F block elements, the lanthanoids, is +3. So +3 is most common in the lanthanoids. However, some elements can exhibit +2 or +4 oxidation state. This depends on this variation depends on the extra stability that they get from the F subshell. So when the F subshell is empty, or if it's half filled, or if it's full filled, you get extra stability. And so therefore, oxidation states can become +2 and +4 respectively. When we're talking about general characteristics, these lanthanoids are generally silvery white soft metals. So their color is mostly silver, and they can tarnish rapidly in air. They are pretty corrosive. Hardness increases with increasing atomic number. So the hardness of these lanthanoids are appreciably strong, and as the atomic number increases, you can find an increase in hardness. Hardness is so strong that samarium, an element of this group, has properties of hardness similar to steel. So it's as hard as steel. When we're talking about metallic structure, lanthanoids contain a metallic structure, so most of them are metals, and they are good conductors of heat and electricity. Now, lanthanoids contain variable density, and they form trivalent lanthanoid ions. And when we're talking about metallic structure, another important point is the melting point. The melting point of lanthanoids range between 1000 degrees Kelvin to 1200 degrees Kelvin. The only exception is samarium, which has a higher boiling point of 1623 degrees Kelvin. Now, the trivalent lanthanoid ions are formed, and these are also colored. Now, the color of lanthanoid ions present in both solid and aqueous state. And they are trivalent because the most important oxidation state here is +3, so they are trivalent, and they also have low third ionization enthalpies. The ionization enthalpies here are low third ionization enthalpies, so the first and second enthalpies may be high, but the third enthalpy is always low across this group. And they are also good reducing agents. So most of the lanthanoids they can be pretty easily oxidized, so therefore they are good reducing agents. And one other thing about lanthanoids is that you can represent all kinds of lanthanoids using the symbol Ln. So Ln is a common symbol for lanthanoids. So when we're talking about chemical properties, lanthanoids react with a lot of substances. Lanthanoids, when they react with acids, they liberate hydrogen, and lanthanoids, they react with halogens to form LNX3 or lanthanoid halides. With water, lanthanoid reacts to form lanthanoid hydroxides and hydrogen. With carbon, lanthanoids form carbides, which are of the form LNC2. When heated with nitrogen, we get lanthanoid nitrides, and heated with sulfur, you get lanthanoid sulfides, and when you're burning an oxygen, you get lanthanoid oxides. So these are the common reactions which are attributed with lanthanoids. So now that we've studied one half of the F block transition elements, let's look at the other half, actinoids. Now actinoids, these have a similar electronic configuration as lanthanoids. The only difference is that the base atom that we use, the noble gas that we use, is radon, and then it is 5F, 1 to 14, 6D, 0 to 2, and 7S2. So those are the second type of transition elements, F block transition elements. These 14 elements are coming after actinium, and that's why they're called as actinoids. So actinium is also included in a discussion of actinoids. Now, the thing about actinoids is that most of them are radioactive, so therefore they do not exhibit a lot of chemical properties. However, you can discuss some chemical properties among them. Ionic size, for instance, gradually decrease along the series. And this is due to the fact that lanthanoid contraction also occurs in the actinoid series. Again, because the f orbital is very diffuse, so there is no shielding effect. In terms of oxidation state, the most common one is +3 as well. However, unlike lanthanoids, they can show oxidation numbers for +4, +5, +6, and +7 too. Now, when we're talking about general characteristics, most of the actinoids are silvery in appearance, and they display a variety of structures. And this variety of structures is due to irregularities in the metallic radii. These actinoids are also highly reactive metals. The condition is that they must be finely divided. So when they're finely divided, when they're porous, they can react very easily. So they're highly reactive. And the irregularities that we mentioned with respect to metallic radii in actinoids are greater than the ones you can find in lanthanoids. Now, magnetic properties here are more complex than lanthanoids, partly due to their radioactive nature. Now, elements here include thorium, uranium, neptunium, plutonium, americium, californium, etc. So these are the actinoid series, the second series in the F block transition elements. Now let's look at what is lanthanoid contraction. So suppose we have an F orbital. The F orbital, which stands for fundamental, has very less shielding effect. So basically, when an electron goes inside, the f orbital is so vast that there is basically little or no shielding effect. So when you go to the next element, it's not just the electron that increases, it's also the proton that increases. So therefore, the atomic charge increases. So the effective nuclear charge increases because of the poor shielding effect. And due to that, you can find a decrease in atomic size in F block elements. So as we move along the lanthanoids or the actinoids, the atomic size gradually decreases. Now, the byproduct of this is that in the D block elements, when we're looking at elements such as zirconium and hafnium, instead of a size increase, you find that zirconium is as big as hafnium, even though hafnium has an extra shell. Now that decrease in atomic size is due to the phenomenon that is lanthanoid contraction, the progressive decrease in atomic or ionic radii from lanthanum to lutetium. And since this also occurs in actinoids, we can also write from thorium to lawrencium. So these are some general characteristics about lanthanoids, actinoids, the D block transition elements, and also some oxides and oxoanions of the D block elements. Now, we said that D block elements and F block elements are really good, have really good uses, so they're used frequently. So what happens when what are the uses that are present for the D and F block elements? Now, iron and steel are some of the most important. Iron and steel are the important compounds in today's world in terms of industrialization. So production of iron and steel is an important process. And D and F block elements have a part in production of iron and steel. And in terms of D block elements, titanium forms an oxide called titanium oxide, TiO. This is used as a pigment in the pigment. This is used in the pigment industry. Manganese oxide, which is MnO2, can be used in dry battery cells, and other catalysts that are used in the industry are V2O5, TiCl4, nickel, etc. Nickel especially is used in the hydrogenation of fats, changing vegetable oil to vegetable ghee. Now, nickel, when in the form of complexes, is useful in the polymerization of alkynes and other compounds such as benzene. So benzene and other organic compounds can be polymerized when we're using nickel complexes. And another very important use of D and F block elements is AGBr. AGBr is used in the photographic industry, and it is light sensitive, and that's why we have dark rooms in order to develop photographs back in the old ages. Right now it's digital, so therefore most of us would not know of it, but still we use AGBr in the photographic industry. So that completes the D and F block elements. So for more of our useful and interesting content, don't forget to subscribe to our channel, Brain Blitz Audios. If you want to access more of our mind maps, then don't forget to click the link in the description down below. So until the next webisode, take care, stay safe, bye-bye for now.